Alright, in this video I'm going to discuss percent composition, and this is going to be a percent composition, oops, there we go, now I have a pen, percent composition by mass. So the percent composition is the relative amount of mass of each compound, so the percent composition of compound X would be the mass of X divided by the mass total. And then we can divide up a compound by all its different elements to figure out how much of that compound is made up of each different element. So this is a relatively straightforward one. Let's just hit an example here. A 200 gram sample of potassium dichromate is analyzed to show that it has 53.2 grams of potassium, 70.2 grams of chromium. Determine the percent composition of all of the elements. So we'll do potassium first. The mass of the potassium is 53.2. The mass of the total is 200. So my percent of that's potassium would be 53.2 grams divided by the total of 200 grams, which is 26.6%. Well, actually, just to make sure we're really clear here, that works out to 0.266 as a decimal point, and then remember to convert a decimal point to a percentage, we multiply it by 100, so that works out to 26.6%. There we go. So times 100% if you want it as a percentage. Okay, chromium is 70.2 grams of the total. See, he's right here. 200 grams. 70.2, so this is going to be 35.1, yeah. 0.351, again as a percent, 35.1%. And now you'll notice it didn't give us any mass for oxygen. But what we can remember is that the total percent composition has to add up to 100. That's the whole point of a percent, right? It's how much out of 100. So when you take everything into account, it has to get up to 100. So it's 100%. So if this compound is made out of potassium, chromium, and oxygen, when we look at all of those different percentages, they have to total to 100. So if this guy's 26.6 and this guy's 35.1, then what's left over for oxygen? Percentage of oxygen is 100 minus 26.6 minus 35.1 is 38.3% oxygen. So we can get a percent composition by taking the mass of that element divided by the total mass, or if we don't have the mass of the element, we can figure out the last element by recognizing that the total percent composition has to add up to 100. If we have the chemical formula instead of a specific number of mass, or a specific mass of a sample, we can solve this problem by assuming that we have 1 mole of the substance. So for example, find the chemical composition of magnesium phosphate. Careful here, we'll write out this compound carefully. Magnesium phosphate, PO4. Remember, this would have had a charge of 3 plus, and this would be 2, or 3 minus, and this would be 2 plus. So when I cross over, this is going to be a 2, and this is a 3. So kind of a big compound actually here when we consider the ratios. So what's the percentage of each element? Well, we don't have a total mass. We don't have a mass for each element, so we have to do something here. We're going to assume 1 mole. 1 mole. Excuse me. So what's the mass of 1 mole? Well, I get 3 times magnesium, which is 24.3. Yeah. Plus 2 times phosphorus, which is 31, plus 4 oxygens, which are 16 each. 4 times 16 plus 31, all that times 2, plus 24.3 times 3. So the total mass of 1 mole of this is 262.9. So I would call that mass total. Now I need to figure out the mass of the individual elements. I really only have to do 2 because once I get the 2, then I can do the third using the 100% thing that I just showed you. So this is the grams per mole, but we assumed 1 mole, so that's what we're going to assume our mass is. So let's deal with, why not, magnesium first. In one magnesium molecule, there are 3 magnesium particles, so 3 times 24.3, which is 72.9 grams per mole. So if I want to know the percent for magnesium, I have 72.9 grams in my 1 mole out of the total 262.9 grams in my 1 mole. So I get 0.277 or 27.7% magnesium. So that's magnesium. Let's deal with phosphorus next. The phosphorus in my sample, there are 2 of them. Remember, I have to bring this into both numbers, so this would be a 1, so bring the 2 in. I have 2 phosphorus. 2 at 31 each, for a total of 62 grams per mole of phosphorus in 1 mole. So my percentage of phosphorus then would be 62 grams per mole divided by my total, 262.9 grams per mole. 62 divided by 262.9 is 0.2358. I'm going to just round that to 23.6%. And then I'm just left with oxygen. So for my percentage of oxygen, I can recognize that they all should have added up to 100%. So if I take away the 2 that I have already, I can see that I must have 48.7% oxygen. Now, it's always nice when I can do a calculation in a couple different ways, because if I can do the calculation in a couple different ways, I can verify that 48.7, and then maybe I'll be very confident that I've done the question correct. So why don't I do this oxygen the old-fashioned way, by recognizing that the mass of the oxygen in 1 mole of the sample would be 8 oxygen atoms, 4 times 2. So 8 times 16 grams per mole. And I still know that my total mass is 262.9. So my percentage of oxygen would be 128 grams per mole divided by my total of 262.9 grams per mole. So that works out to 48.68%, or 48.7% if you round, which agrees exactly with what I got, which means I must have done it right. So, all the way through again, the percent composition, assuming we're doing a percent composition by mass, tells us the relative amount of mass of each element in a compound. So if I take my mass of that element divided by my total mass, I can come up with my percent for that kind of element. So if my mass of potassium, for example, is 53.2 grams and my total mass is 200, then 53.2 out of 200 tells me that 26.6% of my sample is potassium. If I'm not given masses, but instead I'm just given a chemical formula or chemical name, then what I have to do is I have to assume 1 mole of the substance, and then all of the molar masses excuse me, all of the molar masses of the individual elements that make up the compound can be treated as if they were the actual mass of the substance, because I said I have 1 mole, so the molar mass is the mass of 1 mole, so I'm good to go there. The only trick, of course, here being I need to be careful because I don't just have one element or one atom of that element necessarily in the compound. For example, if I look at magnesium here, I have three magnesium atoms in every molecule or every lowest ratio in this ionic compound. So when considering the total mass, I have to find the total molar mass of the compound in the way that I usually do. And then when considering the mass of each individual element, I have to come up with the I have to use the number of that element that I have as well to figure out the total of mass of that element in the compound. So for magnesium, if I had 3, then that means 3 times the molar mass, 72.9, out of the whole 262.9 gives me 27.7%. When I get the percent compositions for everybody but one, since all of the percent compositions have to add up to 100%, 100 minus the other two can give you the percent composition. And we always like when we can do a calculation in 2 different ways, because then we can verify our answer to see if we've done the overall question correctly. So that's percent composition.